Hi, everyone. Thank you for joining today. My name is Dr. Ibe Omodolo. I'm one of the co-founders of Lensa Technology. So what I want to do today is that I'm going to start the first topic in a series that I'm starting. And this series is called Think Like a Process Engineer, Solving Real-World Engineering Problems. So today will be the first of series of topics that we'll be looking at every week. My plan is every week there'll be one video out where we're going to look at a major problem that the world is going through and then use engineering understanding to solve this problem. And again, we're going to be using our software Lensa Sim as a vehicle in which we're going to address this problem, and then we all think together as a process engineer. Are you ready? Let's get started. So the first thing I'm going to do right now is I'm going to share my screen, and you guys can get to know me more, and you can see what is the motivation behind this. Why do I have this authority to be able to talk about this? But anyway, like I said, we are going to be, going through series of topics that we're going to be addressing. And the first one is, can we really solve a major problem that the world is actually going through? But in this case, we're going to be looking at how can we convert the gases that we are flaring and then convert them to useful substance. We're going to be using Nigeria oil refinery or Nigeria flaring generally as a case study here. So again, we're going to be using our software Lensa Sim as a vehicle, and I hope that is really clear. So this, again, one thing that I want you to take out of this and why I'm very excited about the topics we're going to be treating, and why I'm encouraging us to always come every week to watch out for what is going to be released from our YouTube channel, our Lensa Sim YouTube channel. So, but the first one is, can we convert flare gas to liquefied petroleum gas? So that's what we're going to be treating. Now, to give context to this main problem, again, I said I'm going to use uh, Nigeria as a case study here. Nigeria, according to the reports that is available online, is that we've lost close to $56.75 billion since 2022 from just flaring gases. And the funny thing about the whole situation is that Nigeria actually is a big importer of liquefied petroleum gas. We about 1,400% of liquefied petroleum gas are imported into Nigeria. So these are all these are all data that are available online, which I took online to be able to uh, um, properly give context to what the problem is. Okay, so we're going to try to simulate the process and see how really this thing can be done, right? Taking a flare gas to liquefied petroleum gas. All right, so this is a problem statement. You can see the gas flaring situation that we're having, and then you can see what Nigeria has lost so far. All right, like I said, right, why are we, how I said the way we're going to demonstrate this capability is by simulation. And then I want to really convince you right now to understand, why do you need to really understand process simulation, and why should you bother about it? And I know that many people that are going to be watching these videos are going to be a different set of people, from student to professors, right? As a student, I want you to know that what process simulation will do for you is that it will turn the equations and all that you've learned and help you to see the cause and effect before the exam, right? It gives you a real picture of what you've actually studied in class. Simulation is like a virtual lab, let's put it that way. Simulation is the closest you can get to real world situation. And let's say you're already a graduate, right? Understanding process simulation would make you employable, right? And apart from employable, it will also make you innovative, because you are able to think through processes, new processes yourself, try some parameters and see if it's possible to build them. And I'm going to be telling you throughout this whole process, like I'm going to be explaining how this works. Again, if you're an engineer, if you're a professor, process simulation is a core skill that you need to have. And a professor, it's a core skill that we need to teach our students so that they understand how to think new processes and how to even troubleshoot already existing process that is running. All right. To give you better foundation, I thought it is important to explain what process synthesis is, process simulation is, and process design. Process synthesis is a way of thinking like, what should we actually simulate right now? Or, in other words, maybe put it this way, it helps you to decide what the flow sheet should look like. You say, okay, what process should I, to design, or what process should I actually simulate? Does that make sense? Or think up to make it very clear for you is look at the problem that we have right now. Can we address the problem of flare gas? Can we take flare gas to LPG? So process synthesis is the way you actually come up with the flow sheets and say, oh, I will need this, I will need that, I will need this, I will need that. Oh, if I have this is, I'm going to have, I need a feed, right? That will come in. The feed is the flare gas. Okay, I need to be able to compress that feed first and all that, and like that, and like that, and like that. So that's what process synthesis is all about. And through process synthesis, people have been able to come up with innovative ideas, right? Now, process simulation is a way of predicting how the flow sheet will behave, right? Specifying the conditions, the temperature, the pressure. And process design is after um, you've come up with the flow sheet and you have decided the boundaries of the flow sheet, right? Process design is turning the simulated flow sheet into something buildable. Now, can we actually build the plan? I hope that is clear. If there's anything you must take out of this discussion so far, is that process synthesis is a core skill, or better put it for you is that process simulation is a core skill that you need to have. And then, but there's a relationship between process synthesis, process simulation, and process design. They're all together, but I wanted to separate them so that you understand it. Okay, so, but we see that as powerful as these skills, or powerful as these skills is, or as essential they are, many people don't have. They are shut out of it. In developing nation, the problem is that many institutions cannot afford legacy softwares. So students most times are made to go through the pains of solving these complex material energy balances just with their hands. Uh, Sometimes students have opportunity to, actually have this software. I don't know clearly how they get it, but most times it's difficult for students to afford it in developing nations. Use myself as an example. I studied chemical engineering. My first opportunity of interfacing with process simulation was when I was about my fourth year, where some group of students who have finished from the program came to us to kind of, ensure that they pass clearly the information that process simulation is a core skill. So they asked us to, they were running some training and they asked us to pay, but I couldn't afford it at that time. And then I went to do my master's, the same problem. I didn't have the software. I didn't learn it. My PhD, when I came to study in the US, I had to also use that skill in my work, but I wasn't versatile enough. I don't have a broad understanding of process synthesis simulation. I had to ask someone to help with the whole simulation itself, and then we collaborated on that research article. All right. So you see the challenges I went through, and that's the challenge. This is the same story for many students from developing nations. They don't have access to this simulation, and because their institution cannot afford it. But then you are saying, okay, what about developed nations? Yes, developed nations like the US, the UK, they have access to this legacy software because their institutions are able to purchase the student version for the university, and then the students are able to use it. But here comes another problem. After the students leave the university, the licenses expire, and there's no way for them to show what they have built. And that's how we came up with the whole a better product. No, I take my word back. Not clearly a better product. I would say a product that is accessible. I don't want to use the word better product here. Permit me from using that word. I want to make it very clear. We try to solve this problem in sense that we created a software that is able to that is available for everyone. And I'll show you what I'm trying to say now in the next slide. So we created Lensa Sim. Lensa Sim is our attempt to democratize process simulation. We created a web-based or browser-based process simulation. It's just like bringing process simulation to everyone, bringing it to everyone clearly. And so you are able to simulate, right? It does not require the complexity that we see with legacy software, whereby you have to install it and all that. That is not the problem here. You are able to even browse from your phone, and you're able to build real-world flow sheets. And like I said, like in developed nations, students have access to that, but they are not able to provide a proof of their work, right? So we created Lensa Connect. Lensa Connect is a way that after you build the software, you are able to publish the work on our website. And then recruiters are able to see what you've done. So they can actually hire you for what you've done, not what you've just written on your resume. I hope that's clear. Okay, having talked about the importance of process simulation and how we try to solve this problem by creating Lensa Sim, I want to now go ahead to demonstrate the capabilities of this software using it to solve real-world problem of taking flare gas clearly to liquefy petroleum gas, taking flare gas to liquefy petroleum gas. All right. Okay. Join me now. So here we're going to do the live demo. We have the flare gas here. The flare gas that we're going to be um, dealing with here is the one that is already sweet and dry flare gas. So for the case of teaching today, so you can go ahead and scan this QR code, or you just go to your browser and type www.lensasim.com, and then it take you to the software. Okay, so now let me do the same thing right now. I'm going to show you, let me share my screen. So you see what I'm saying right now. Give me 1 minute. Okay. Okay. Um, let's share the software right now. Good, good, good. Okay. So this is Lensa Sim. All right. So when you come into Lensa Sim, the first thing it will ask you to do is to sign in, right? You would, or maybe let me just do that so you see what I'm saying. So when you come into the website, the first thing is it brings out the sign-in page. So all you need to do is to hit that, to click that, and put in your email address, any email address that you have. And when you click email code, it's going to email a code to that email address that you provided. So for me, I'm using my Lensa Sim email address. So now I go and get the code that has been emailed to me. Going to get the code now so we can sign in easily. All right. Okay, let me sign in. Okay, so I'm all signed in right now. So now let me open the simulator. Let me open the simulator. So let me share, because it's going to open on a new tab. So I need to share that right now also. So we all see it. I need to share the new tab that has just been opened. Okay. Good. Okay. Okay. All right. Okay, so now the first environment it brings you to is the simulation, this environment whereby you have to specify the component. The first thing is you need to specify the component that you want to, that is present in the feed that you want to work with right now. Now, one thing I want to quickly say is that our simulation has a guide tool, right? It will guide you. Especially if this is the first time you're using it, you're able to, it's going to guide you on what you need to. For instance, it says telling me pick your component. Okay, let me turn it off. But if you are using this for the first time, I think that will be helpful for you to start it. Okay, now let's start with specifying the component. Like I said, I'm going to be working with what I call, for the case of study, I'm going to call it like a sweet and dry, sweet flare gas that is dry, and then they remove most of the contaminant that is there. So for this case of these studies, based on the data that we've tested, I'm going to use that to demonstrate this capability. All right, so let me specify the component. The first component I want to specify here is nitrogen. So if your component, you can just go to this search bar here and specify them. The first component that is part of my flare gas feed is nitrogen. All right, so the next thing is methane. Methane, so you can join me along here. Methane, choose methane now. Now followed by ethane here. Ethane, and then propane. Propane, propane here. Now the next component that I would like to specify is butane. So let's put isobutane and then my normal butane here. Normal butane. Let's look for butane, just pure butane, just normal butane here. Selected. So the next thing in component that I'm going to need to specify is pentane and isopentane and its isomeric form. So let's get to pentane now. So you have to look for pentane. Pentane. What? I don't see pentane. It's actually there. I'll show you now. So iso. Let's get iso, maybe because we need both the pentane and the normal pentane and the isopentane. So let me specify them. So there's, okay, that's not isopentane. That's isopropane. Okay. Isopentane. Yes, this is isopentane. You specify isopentane here. So let me find pentane. I need pentane itself. So this is normal pentane. Also, yes, specify here. Okay, I'm almost done. Then the last component that is in my, this is hexane. It's hexane, normal hexane, normal hexane, normal hexane. Okay, now I am done specifying my component. The good thing about software is that it's going to guide you, like I said. Now, based on the component I've specified, it's suggesting to me that the best equation of state to use to properly model this will be Penn-Robinson, and which I agree. So as a process engineer, this is how the process engineering thinking come in place. You have to really, decide based on the component that what equation of state will fit. For this, Penn-Robinson, so I agree with Lensa, so I will take Penn-Robinson and then continue to the simulator. So now it brings you now to the simulation environment for you to do your simulation. All right, as a process engineer, the first thing which we need to do is to put the feed, right? We already specified the feed. So I'll come here now and take my feed here. So you see, this is the feed now. Now, for feed, I need to specify the condition at which the flare gas is coming. This flare gas is going to be coming at 35 degrees centigrade and a pressure of 10 bar. Okay, you can get data from from literature to specify what you want. For the case of these studies, I'm using a flare gas that is coming at a temperature of 35 degrees centigrade and has a pressure of 10 bar. Now, its molar flow, it's 100 for this one. Its molar flow is 100. So let's put that molar flow is 100. Okay, now we need to calculate the mole fractions, right? These data are available, right? You can get the data from literature or from gas analysis, the type of conditions that your feed will come in from. So from there, we'll go on from here. So for the case of this study, I'm going to specify from what I have from literature is that the mole fraction of nitrogen that I have will be very small, like 0.01 for nitrogen, 0.01. And then I'm going to have a methane of 0.7. Methane of 0.7 here. And then I'm going to have ethane of 0.1, 0.1 ethane here, 0.1 ethane here. Let's go on. Ethane, then propane. Ethane is 0.1, a propane of 0.08, a propane of 0.08 propane. So again, let me, for case first, nitrogen is 0.01, methane is 0.7, ethane is 0.1, propane is 0.08, isobutane is 0.03. Okay, like I said, these are data from literature. You can always get from literature what you want to use. Okay, then normal butane of 0.04, normal butane of 0.04, normal butane of 0.04. Isopentane of 0.015, 0.015. Same here for pentane, 0.015. And then my hexane my hexane is 0.01. 0.01. So you need to normalize it so that everything is 1. All right. Now we've specified the feed. The first thing in process simulation or process engineering, as the case may be, is to specify the condition of the feed that is coming from here. So this feed, which is the flare gas, is specified. All right. Now, again, let me bring you back to our problem. Can we convert the flare gas to LPG? And liquefied petroleum gas that we're more concerned about is propane and butane. Is it possible for us to get this propane out of this gas? Because at ordinary pressure, most of the components here are going to exist in gas phase. So the question is, what do we need to play around with? What property do we need to play around with now to be able to tweak this feed in such a way that we can condense out the heavier ends, right? So because at ordinary pressure, they are behaving in gas phase. So one property we need to play with, two property, is pressure and temperature. Because when we apply high pressure to the feed, we put the feed in a condition whereby we can easily condense out the heavier ends. So for us to be able to do that, I will need a compressor. So compressor is what I'm going to need to be able to compress my feed. So you add a compressor now. So what the compressor will do is to compress the gas such that we can liquefy the heavier ends. So now that I put a compressor, I need to specify the condition of my compressor. So this compressor is going to take my feed to a condition whereby the outlet pressure is 30 bar. So you're going to specify that. Again, you need to make sure that you have the right unit. So this is now 30 bar now. And then there's a problem with compression. Once you compress a gas, meaning that you have applied high pressure, then you are going to also affect the temperature. So the temperature will now increase because pressure is proportional to temperature, right? So remember why I'm compressing. I'm compressing because at ordinary pressure that I have, my components are in gas phase. But I want to compress in such a way that I am able to get the heavier end and to liquefy them out, right? So now that I have compressed it, now the temperature is now high. So I need to remove the sensible heat. So what do I need? I need a cooler. So I put in a cooler here. This cooler will help me to remove the sensible. So the cooler will bring it back to the temperature I started from, which is 35. Okay. Is that really clear? And I want you to really get what we're saying here. I explained that compression has increased my temperature high, so I need a cooler to cool it out. So this first cooler is just going to remove the sensible heat. But remember where we are going. We want to be able to cool it so much that the heavier end can liquefy out of it. So we need another cooler. In this case, it's going to be a chiller here. So I'll connect a chiller here. And this chiller is now going to do the work of refrigeration and cool it so much that I can easily liquefy the heavier end. So this chiller is going to be operating at minus 20 degrees centigrade. Now we have done something. We played with pressure and temperature, right? And because we've done that, we have cooled it so much now. Imagine that what is coming out from this cooler now is vapor liquid. So we're going to use a separation technique whereby we are able to do a vapor liquid separation, right? So we need a flash drum here. So I look for flash drum here. So this is a flash drum. I connect my flash drum now here. So what does the flash drum do? It's just going to separate them into two phases such that my gas phase here, this gas phase, which is more of ethane and methane, should come out here. So more of the gases, and then I have my heavier NGL, natural gas liquid, that are going to be coming out from here. Okay. Now what I've done is two-phase, but I need to specify the condition of my my flash drum now. So this flash drum now, remember, it's not changing the temperature, right? The temperature is still going to be the same way. The temperature is coming out from the chiller. So it's going to be at minus 20. The pressure, let's assume the pressure is still close to where it was before, 29.4 bar. So what this has done, let's do it this way so we create more room. Okay, I hope you are getting where we're going now. We're going to really, think like an engineer now and fix this problem. You see how we're engineering this problem right now, situation. Okay, so we have a bottom that is coming here, which is majorly what? Liquid. But then mostly liquid, doesn't say that everything. So we did a vapor liquid separation here. So the flash drum, I've taken out the gas phase here. And then we're having a liquid phase coming out here, right? Okay, so this liquid phase now is a natural gas liquid. It does not contain fully what we want. So we need to do something to this liquid phase. So this liquid phase needs to go to another separation technique. But before we do that, there's a problem. Remember, the pressure is still high here, 29.4 bar. So we need something that can bring it to a lower pressure. So we need a valve here. So I'll look for a valve. Where is my valve? Where is my valve? So this is your valve here. This valve is going to help us to bring this to lower pressure, say like 18 bar. Let me see what I have in my document that can help us. Yes, it's going to bring it to 18 bar for us. So now you have your natural gas liquid at a operating condition that is safe enough to send it downstream to the distillation column. Okay, so we need a distillation column because we have a mixture of component that is more than one, and to properly do distillation, we will need a distillation. But I'm not going to use a shortcut. You understand that shortcut distillation, it's what we use to, as a way we start from to optimize the process to decide how many stages do we need, how many of these how many of the stages, what should be the reflux ratio, and all of that. So because I've optimized the system in a way that is easier, I've tested it. So I'm going to just do the fractionation itself, use a rigorous distillation and connect this to the rigorous distillation here. Okay. This is my rigorous distillation here. Okay. So it's a rigorous distillation that I'm going to use now to do this distillation. Okay. Now, does it make sense? Now, what is coming out from the valve is my natural gas liquid that is entering a rigorous distillation column. Now, for the case of these studies, I've optimized, like I said, I've used the shortcut distillation to optimize the condition I need for my rigorous distillation. So I'll just put in those things and I'll explain as I do that. For this, I'm going to use a total of 12 stages, and the feed should come in from the 6th stage here. The reflux ratio that I will need here is 2.5. Okay, now for here, I don't need a total distillate because I still have some gas that is coming out. So what I'm going to do is partial vapor distillate. The reason is that so that I'll explain more now. And then we change this one now from distillate to bottom rate here. And I'll explain more. Okay, now let me put the condition where I talk us through what we are doing. So for a bottom rate, we are going to use the bottom rate of 15 here. Bottom rate of 15 here. And then good. Okay, what have we specified? We specified this one, we specified that one. All right. We need to put the condenser pressure. So let's put the condenser pressure and the reboiler pressure here. Okay, so my condenser pressure is 1000 kilopascal here. So here is 1000. Then this is 1050. We can convert it to bar. Okay, now let's walk us through this. Now, the first thing is that we don't need a total condenser because we still have a mixture of gases that we want to separate out. So we're going to use a partial condenser, which is just going to help us cool the process, right? The main property through which separation takes place is by volatility, right? We use the volatility of the component, right? So I want to clearly mention that the condenser we need here is not going to be a full condenser because we have gases that are still here that needs to come out from as the distillates. So if we do a total condense, that means we want everything to condense, which is does not make engineering sense here. Okay, does that make sense? All right. And I said that we should also choose bottom rate here. Let's show you where I chose bottom rate here. The bottom rate here is because my desired product is in the bottom, right? So here, the product that is going to come out from here as my distillate is still gases that I don't need. And I'll show you. I'm going to simulate this first, and I'll show you. And then the product that's going to come out here is my distillate. Yeah. Okay. So let me put the guide on now. You see, if I had the guide on, it's going to walk you through the process, but I always put it up. Okay. All right. Amazing. So let's run what we have right now. Let's see if it will converge. Let's see if we've made any. I will advise you that whenever you're building a process, as you continue to build the process, please continue um, to test it and see if it's making any engineering sense. Okay. All right. Um, okay. So now I want you to focus on the product here, and I want you to focus on S8 and S9, and that would explain some of the reason of what I'm trying to say here. So if you come here, your S8 here, my expectation is that it will have more of the gases that I don't want. Remember, we have nitrogen, methane, and all that. So if you come to S8, you see we have a lot of gas, nitrogen, more of the methane is coming out here, more of the ethane is coming out, and it has less of our desired products. And most of our desired products here are in S9, right? So now the S9 is what is still your it's still a mixture of your desired products, even though you've been able to successfully remove most of the gases like ethane and methane out. But what is coming out from the bottom here still has methane, still has well, a very trace amount of methane and ethane, but it has your liquefied petroleum gas, which is your propane and butane, but you still have heavier end as pentane, hexane. Those are heavier end. Those are not your desired products. So because of that, we need a second stage distillation, right? Does that make sense? We need a second stage distillation. Okay. Now, to do that, we need another distillation column so that we can properly separate the natural gas liquid I have and separate them into components and get our desired component. So what I will do now is that I will delete this here and put another distillation column here, another rigorous distillation column here. So this comes in here. And then, like again, we need to specify. So like I said, I have optimized it to what will give us very close to it. But I will give you I will expect I will give you some call to action, what I expect you to do. But one of them is that I need you to simulate this process again yourself and try different number of stages and tell me if you got something better than what I have. I'm showing. All right. So for this case now, the second distillation column would have 15 stages. 15 stages, and we're expecting our feed here, which is the bottom from the first distillation column, to come in from let me see. Okay, yeah, I said it's coming from stage 8 here, and let's see what's my reflux ratio here that I've optimized. My reflux ratio is 1.7. So for this case, I need a total condenser because I want to liquefy everything now. I want to liquefy everything now. So because my desired product is going to come out to as liquid, right? I want to liquefy. I want to liquefy most of, so that, let's put it, I want to liquefy it as much that most of my heavier end will come out from the bottom and my desired product will come out as distillate. All right, so I can use the total condenser here. So what should be, in this case, what is my distillate rate here? My bottom, so total condenser. So my distillate rate is 10 kilomoles per hour, and then I'm using a pressure of, so let's put a 10 here from what I've optimized, 10 here, and then let's put my condensed pressure and reboiler pressure here. So my give me a minute, let me see what I specify. Again, play around with this, please. So my condenser is 750 kilopascal here. This will be 750 here. This will be 800 here. Now, I need to explain something that I did not explain in the first. So you need to understand that as you are specifying this, always make sure that your reboiler pressure is higher than your condenser pressure. And this makes sense, right? The way the whole separation happens in distillation column is that the gases are going upward and the liquid are going down. The gas should have enough pressure to overcome the barrier of the condenser pressure that is high. So that's why we want to always make sure that the reboiler pressure is higher than the condenser pressure. The reboiler is at the bottom, right? And the condenser is at the top. So the gases are coming. They need to have enough pressure to overcome the barrier. So they keep going through the stages of the distillation. Okay. Now that we specify the second distillation column, so let's put connect the outputs here. My distillate is here and my bottom is here. So now that everything is specified, let's run it. Let's run it and see how this goes. If it's going to converge, as a process engineer, your first solution is not just did it converge, but good, this one converged, but then does it make engineering sense? A process engineer needs to think through. We had a problem statement: take a flare gas and take out the liquefied petroleum gas. How can we solve the problem Nigeria is going through right now, or the world? But again, I'm using Nigeria as a case study, whereby a lot of gas flaring is taking place, but yet people don't have enough cooking gas. So can we take those gas and turn into cooking gas? All right. Now let's see if this, yes, it converges, but does it make engineering sense? So I need you to focus on S10 and S11 here right now. S10 and S11. Okay. All right. S10 and S11. So let's see what we have as our component here. Remember, S10 should have my distillate. And in this case, my distillate is my liquefied petroleum gas, which is majorly what? Propane and butane. While the bottom should have more of the heavier hands, like my pentane, my hexane, the ones that I don't need as its case. So focus on S10 now. Your S10, look at your propane. You see you have about 0.498%, 4.4988 more fraction of pentane, and then look at butane, very good, and we have little amount of heavier hands, which is isopentane, pentane, and hexane. But when you come here now to my bottom here, you see we have more of the more fractions here is higher. So this clearly proves that what is coming out from here, which is my S10, is majorly my desired product, more because we have very small amount of of this nitrogen, very trace amount, very small amount, but then we have more of propane, butane, and isobutane, right? I'm happy to let you know that with what we have done today, we have successfully demonstrated that we can solve the problem that the world is going through. And this is how process engineers actually think, right? Being able to solve this problem. So now that you've simulated this, I was mentioning that two problems that we see currently that chemical engineers, students, and chemical engineering graduates have. One is they don't have access to, in developing nation, they don't have access to powerful simulation software to help them to, demonstrate their chemical engineering capabilities, right? Most of them just do the strenuous work of doing the calculation with their hands. While in developed nation, they have access to this software. But the problem for them is that how do you show that you built this, right? How do you? So that's why we build Lensa Connect. So after building this now, I can actually just, so if you look at our software here, look at this as just like a globe. You see publish to Lensa Connect. You see that? But to make it very nice, you can, specify this. Come here, it said untitled simulation. Give it a name and say, for this one now, we say, I can say solving problem, maybe the solving problem of gas flaring. Let's give it a name. Oh, just give it what you, maybe you can say converting flare gas to LPG using Lensa Sim. Yeah, anyone. So whichever one works for you, Lensa Sim here. Or I'll just put it maybe converting flare gas. So after you've given it a name now, so you come here and save it. So it's saved to cloud. So it's saved now. So you can come back here. This looks like a globe, and then you publish it. Right. So now that you've done it, it's already gone to Lensa Connect. I will show you that now. And that's the last exercise I'm going to do. So let me stop sharing the simulation environment and share Lensa Sim right now. Give me 1 minute. Okay. All right. So I'm going to stop sharing here and I'm going to share the Lensa Connect. Before that, actually, let me show you how to go to Lensa Connect. So I come back now to our simulation, our website now for simulation interface. So you see, so you come here to connect, just click connect here. So I'll show you now. Connect here. Okay. Again, it is going to open on a separate tab. So I need to share that tab. All right. So now this is Lensa Connect. So share Lensa Connect now. Okay. Now, so you see, this is Lensa Connect. See, what you publish already shown straight. You see, so you see what we just did together in this tutorial now. So with this way, it's easier for you to show, recruiters what you built, right? So you can see, this is what we built together in this class, converting flare gas to LPG. So if you are a recruiter here, it's easier for you to search for somebody who actually understands chemical engineering, but I'll come to how recruiters can do that. But you now, so this is me now. So you come here, you see my profile. You see, you create your own profile, put all the details. So you see, it shows all that I've done so far. You see my profile here. It shows this. Now, a recruiter can read, so it's easier for me to justify that I understand, chemical. This is now I've demonstrated my understanding of separation. Generally, I use the flash drum, I use my distillation column and all that. So I demonstrate. So whoever is hiring, so if you come here, you see hiring. If I click here now, recruiters can easily search for people's name. Let's say search for eBay and quick search. And then you can find me and see all, it sees my profile, it sees everything that I've verified. Now, I hope you really understand what we've done so far. And I'm really excited for starting this journey with you all, using Lensa Sim to solve real world problem. And then until then, I want you to, until we meet for the next class, what I would like you to do is you try to also, simulate something. You can first simulate what I've done so far, converting flare gas to LPG. And then, so you also try to do that or simulate something else. But the challenge we have in this series is we want us to begin to think like an engineer, solving real problems, not just complaining, why are these people flaring gas everywhere? Can you think of a way you can, simulate that process and justify something that you can, propose to the government? You never know. You may be able to, solve a major problem that the world is going through. And that's what the simulation is going to help you, right? You don't want to try this in real plant, right? You need to, like for us, for me to finish, we need to specify a lot of things. Actually, again, for today, what I've done so far, just the steady state simulation. We have a dynamic simulation, but I didn't do that today. But for the interest of time, and this is what I'll focus on today. I hope you learned something. I have a series of topics that I want us to go through, but if you have any other topic that you prefer us to deal with, you can suggest that in the comment section. When you go through this video, suggest that in comment section. And then, yeah, again, remember, you can just easily use the software. Go to www.lensasim.com and then you start the simulation. And there's a free version for students that you can use, but it has limited capability. But if you go to the website, you see all I'm saying. But then if you want, bigger future, for instance, now, right? For instance, for this class now, I did not do the techno-economic analysis. I only just demonstrated that we can use simulation to prove that it's possible to take flare gas to LPG. With time, I'll begin to show the techno-economic analysis. But yeah, I just want to be using simulation to demonstrate steady state, with time, I also do dynamic because our software has a dynamic simulation capability also. Yeah, so I hope you enjoyed this class. I hope you learned something new. Again, my name is Dr. Ibe Omodolo. I'm one of the co-founders of Lensa Technology. And then our product, what it's doing generally, that we democratize process simulation, trying to, solve the challenge that people are going through. But like I said, we created a full ecosystem, right? We want you to be able to build your simulation, build your portfolio, and then publish it. That's why the whole Lensa ecosystem itself. You use Lensa simulation to build your simulation. Lensa Connect itself is where you publish your work so that recruiters can, like I demonstrated for you easily, how recruiters can search for people. Recruiters can see what people have been able to publish over time. And then as you put in that, we're expecting recruiters to come into Lensa Connect and begin to see people who actually understand chemical engineering, not people who just wrote, things on their resume. I hope you learned something new. Again, this series is Think Like a Process Engineer, solving real world engineering problems. And like I said, every week we're going to solve real world problems. So this the first one we are releasing this week, and then we're showing you the capabilities of our software and how you can use to solve real world problem. Expect this is going to be a long week, and I'm expecting that by the end of this whole series, you have now become a very, very strong chemical engineer solving real world problems. All right. Thank you. I'll see you next time when we release the second video. Again, feel free to drop in the comments what video you would like like us to do next. If there's a real world problem you want us to use our simulation to do, let us know. We'll address that. All right. Bye for now. You take care.